So let me continue with a few more facts about norms on vector spaces. Actually, the norm we are concerned with here is the operator norm on the space of linear transformations. So let's go back to that setup. So here's the last time I had proved that the operator norm is indeed a norm. It satisfies the defining properties for a norm that I mentioned last time. Now let's note one very crucial property. If S belongs to L, Rn, and so, in other words, if I'm able to compose two linear transformations, then the norm of the composition is less than or equal to the product of the norms. So, in fact, this is one of the main reasons why one works with this operator norm. There are lots of norms on any finite dimensional vector space, in particular L, Rn, Rm, but this specific norm has this nice property, and that turns out to be very useful. The second thing is, this is one thing, second thing is other ways of sort of slight variations of the definition of the operator norm. They're all equivalent. So let me mention these. So norm, the operator norm of T can also be written as sup norm Tx. I can, instead of taking the sup over all x whose norm is less than or equal to 1, I can confine myself to unit vectors. And in fact, I can also do the following. I can take norm Tx, divide by norm x, and take the sup over all non-zero vectors. So we have three ways of writing down the sup. They all give the same answer. So let me start with the first one. The multiplicative property. Actually, all of these are quite straightforward. So let's take x, let x belong to Rn, norm x less than or equal to 1. Then Ts of x, norm of this, is equal to T of S of x and this, we have seen that this is less than or equal to norm T multiplied by norm S of x. And again, a similar inequality for S of x will imply that this is less than or equal to norm T, norm S, and then norm x. which is, since norm x less than or equal to 1, this is less than or equal to norm t times norm s. So norm of ts of x is less than or equal to norm t times norm s. When I take sup of the left hand side over all x with norm less than or equal to 1, I get the required inequality. Therefore, norm ts less than or equal to norm t times norm s. So that proves 1. And as for the second, let's take, right. So what I want is, the claim is that sup norm x less than or equal to 1 of norm t of x is equal to sup norm x equal to 1 norm t of x is equal to sup x not equal to 0 norm tx by norm x. This is just an exercise in the definition of the supremum of a set, and of course the only property that we need of T is that it's linear. Linearity and the definition of sup will give all three these two equalities. So I won't prove this. I leave it as an exercise. In fact, we have already seen in the course of the proof that the first equality has already been dealt with, and the second equality also we have seen right in the beginning. So I'll skip this part. So I'll write it as check this. Now let me make a couple of remarks about distance functions of metrics. I'll have to talk about that soon enough, but let me introduce this now. A metric or a distance function on a set X is a function d from x cross x to r, 0 infinity, satisfying distance between x and y is greater than or equal to 0 for all xy, and this dxy equal to 0 if and only if x equal to y. The second property is distance between xy equal to distance between yx for all xy. The third one is the triangle inequality. Distance between x and y less than or equal to distance between x and z plus distance between z and y for all x, y, z. Well, so what I wanted to say is, note that a norm on a vector space gives rise to a vector space, let's call it V, gives rise to a metric on V. So we just define the metric to be dxy is equal to norm of x minus y. So let's quickly see that if I define a metric like this, it is indeed a metric in the sense that it satisfies the three properties. Well, the first property, dxy greater than or equal to 0, is norm of x minus y greater than or equal to 0. And the norm is 0 if and only if we know that the vector is 0. So that happens if and only if x equal to y. And as the second one is also quite straightforward, we know that norm of x minus y is the same as norm of y minus x because of the scaling property of norm. As for the triangle inequality, one and two are clear. As for the triangle inequality, what one wants to check is norm of x minus y. Is it less than or equal to norm of x minus z plus z minus y? So we want this. And this is immediate from the definition of the norm, because I can write the left hand side as x minus z plus z minus y, and the third defining property of a norm will tell me that this is less than or equal to x minus z plus z minus y. So this proves that a norm gives rise to a distance function on a vector space. And even though we will need it for now, let me mention something even more sort of restrictive on a vector space, namely an inner product. So an inner product on a vector space is a function, so I'll denote it by this kind of bracket, from V cross V, vector space V, to R. So the inner product of V comma V is always greater than or equal to 0, and V is 0 if and only if V is 0. The second thing is that V, the inner product of V and W equal to inner product of W and V. Now here I'm working with real vector spaces. If I had a complex vector space over complex numbers, I would have to modify this second condition a bit for all VW. The third property is that this inner product is supposed to be linear whenever we fix one of the, see, the input for an inner product is two vectors. If I fix one of the vectors, I'll get a function from V to R, and that should be linear. So alpha v1 plus beta v2 w equal to alpha v1 plus beta v2 w. And the fact using 2, one can see that in fact the same property holds. Here I fixed the second variable, vector variable w, and I got linearity in the first one, but the property 2 will imply the same thing. So let me write it down anyway. V alpha w1 plus beta w2 equal to alpha v w1 plus beta v w2. Now note that the next observation is that an inner product gives rise to a norm. Namely, you define the norm of a vector to be just, this is a definition of the norm arising from an inner product. So I just take V inner product V and then I take square root. So in short, to summarize, and one has to check that this is the definition. One can check that this is indeed a norm. Now, what is not obvious on the face of it, the triangle inequality, because in the definition of an inner product, there is nothing which resembles a triangle inequality. In fact, the only place where we have an inequality is the first one, that the norm of that the inner product of V with itself is greater than or equal to 0. But that combined with this property 3 and 2, one can in fact prove the triangle inequality for the norm defined like this. So that's a small exercise, but that does require a proof. So to summarize, inner product, from an inner product I can get a norm, and from a norm I can get a distance function metric. The inner, note that an inner product or a norm makes sense only on a vector space, while this last one, a metric, is a very general thing. The domain can be any set. So excuse me. Right. So inner product, and then what? Also, it's. One should note that these implications are not equivalences, in the sense that, for instance, having a distance function on a vector space will not give rise to a norm, or for that matter, having a norm will not give rise to an inner product. So I leave it you to come up with simple examples, but let me just point out one one class of well-known examples of norms which are not inner products, which do not come from inner products. Norms on Rn not arising from inner products. So this is the so-called LP norm. So what one can do is, let norm of x, the pth norm of x, we define it to be sigma mod xi to the power p I equal to 1 to n, and then take 1 over pth root. So here x equals x1, x2, xn. And here I can take p to be, let me take p greater than 1. So for any p greater than 1, I define the xp to as in this fashion. For p equals 2, it is something that we are familiar with. It's just the Euclidean norm. So this is just I square it and then take the square root. And I know that this is just the square root of the standard inner product on Rn. So for p equals 2, it is indeed the case that this arises from an inner product. Now one can check that for p not equals to anything other than 2, this norm does not arise from an inner product. And in fact, there is a very simple criterion called the polarization identity, which will tell you when exactly a norm arises from an inner product. So it's a necessary and sufficient condition. But all this is not really needed for what it's just, I'm just mentioning things which you're bound to encounter sooner or later in your study of mathematics. Okay, so let me end this lecture at this point, and then next time I'll talk a bit about matrices.